So, as Marion said, Liz Varga from University College London. This is work that I've done in collaboration with a number of other colleagues who are part of the DAFNI wider team. So thank you to DAFNI for the funding for this work, and also thank you ultimately to EPSRC who funded the DAFNI and indeed UCRIC projects. You'll see we also are collaborating with John Batterby, who spoke earlier on from Costain, and also Ben Kidd from Arup. So I wanted to start this talk by describing or finding a definition which I thought was really useful for ontologies. And this is one from Struder from 1998. And what he says is that an ontology is a formal, explicit specification of a shared conceptualization. Now, to unpick what that means, we're going to look at the terms in the definition in reverse. So we start with the conceptualization. So basically, a conceptualization is something abstract. It's not the real thing. It's a representation of some phenomena that's in the world, but it's got relevant concepts that we pick out from that phenomena to create a conceptualization. So it's a number of things that are in the domain of interest. The fact that it's shared means that we have some agreement, there's some consensus about that conceptualization, that we have some belief that it's correct. In terms of the explicit, so we have a formal explicit specification. Explicit means that we have constraints on their use. We describe what's in scope and what's not. So we have a very explicit constrained definition of what they can do. Now, formal also means that it's machine readable. So basically, it excludes natural language processing and really refers to rules and axioms that we can then implement into an electronic digital environment. So if this ontology is, if you like, it's a formal description, it's a way of describing something that's in the real world to some degree of interest. So this is work developed by the team at on this DAFNI Infrastructure Research Ontologies project. In particular, I want to mention Lauren McMillan, who's created this visualization and indeed the underpinning work. So what we've looked at here is what are the ontologies, what are the types of ontology in the infrastructure and cities scope. And so here, indeed, we have this overlap of computer science, because we're actually, this is an implementation into computer science. So all these ontologies are relevant for computing, but we have the overlap with philosophy, whereby we have these foundational top-level ontologies, and these are the ones that Chris Partridge has been discussing. Now, when we look at the domain of interest, so this could be an energy system, a transport system, or indeed a water, energy, food nexus, whatever the domain is, we have domain ontologies. Now, where domain ontologies are different from top level is that they describe the components of that domain. They overlap with the top level ontologies in terms of these middle ontologies, which have aspects of both domain and top level. Different from domain ontologies are applied ontologies, and these are very specifically purposeful, if you like, tied to use cases where we try to describe the particular actions for an application. So it might be a traffic management system, or it might be a water flood management system, but it's applied, it's purposeful. So it brings aspects of the domain into the applied, but it also brings aspects of the device into the applied technology, because the devices are the sensors that are actually providing information to make those use case and purposeful decisions in the applied ontology. Now, what's important about these different types of ontology is that the top level ontologies have more generality, or have more of the general structure of the concepts and relationships in our domain that can be then used by others. But we need to agree on what those top level ontologies are if we're going to use them across the piece. And you can see that as you head towards applied ontologies, we get more and more specificity, as in there is more specific knowledge relevant to just that part of the application of that ontology. So these can be very much managed in a distributed way, whereas the top level ones need to be much more common and shared across all users. Now, I don't want to dwell on this one, but these are specific examples in energy, water and transport of ontologies that we've discovered, a bit like Chris's work on top-level ontologies. And we see some of these BFO, the Dolce, the Borough, all these ones are top-level ontologies. But you'll see immediately that the top-level ones are different. So when we look in water, they're not the same as those in energy. So if we want to have a federated digital twin across all these sectors in infrastructure, then how are we going to reconcile these different top-level ontologies? Just before I move on, I want to mention that you'll see the cyber physical systems, they both have, they all use SSN, which is the semantic sensor network ontology. So that bodes well actually for the feeds from devices and for actuators. Now, just back to these top-level ontologies, if I look at Matthew's and Chris's work on this, the ontological commitments in the report from CDBB on the top-level ontologies, we see already that these three top-level ontologies used in water, energy and transport do not have the same ontological commitments. They have some shared commitments, but they're not all the same. So one of the activities will be to reconcile these or to work out which ones should be taken forward. And of course, that is part of the work of the information management framework going on forwards. Now, I just wanted to reflect on the fact that actually our systems are not static. Usually ontologies are static representations. So this is one of the big challenges for ontologies, is how can we make them dynamic? The world from Victorian times does not look like the same world as today's world. And indeed, I don't even have a picture of the future world because we don't know what the future world will be like. So our ontologies need to evolve. So we need to have a mechanism for ontology evolution. And what I'm arguing is that actually digital twins creates that capability to evolve our ontologies. So heading towards digital twins there, already we know that we have the SSN ontology, which is great because they can be almost adopted immediately for digital twins. We know that the twins are going to provide bidirectional feeds of information, primarily to aid our understanding of what's going on, but supporting decision making. But obviously we need those twins to then manage this evolution of our understanding. So how can our digital twin representation of the real world evolve with the data that we're getting from digital twins? And indeed, one of the second biggest challenges, I think, is about managing this interplay of scale. How can we manage having a view of both the city scale and also the household scale, depending on what our particular interest is at any one time? How can we resolve between scales, and indeed not just geographic, but also temporal scales? So two just very quick slides on examples of ontology that we've looked at a bit more detail. This iCity ontology, which was developed by Mark Fox in University of Toronto, has tried to bring together all the different city ontologies, including for transport, for energy, and so on. And these are, if you like, the domain ontologies. And underpinning those are foundation ontologies, not quite the same as what we have from the top-level ontology work, but sort of similar, because we talk about land-based, about date-based, time-based, and so on in these foundation levels. But you see the foundation level underpins what we have in domains. It also works, builds on other work that, that Mark has done and others have done on these different standards and ontological descriptions. And my final one is just to reflect on John's description for the smart motorways, because the use case for our project that we're sort of trying to see how we can support with this ontology work is to try and see how we can bring together this world, this modelling this world of connected automated driving systems. And so what we want is some holistic real-time ontology of this domain. We don't want it to be car-centric, nor road-centric, nor route-centric, nor driver-centric. It needs to be the whole system. It needs to have some context awareness, a little bit like human reasoning, but it has to address these interdependencies. And there are several ideas that are coming out about how we can do this, but it's a massive challenge because of the legacy, the history of how we've evolved so far, and it's giving us a clue about how we might want to evolve for the future.